Okay, let's get started. Last day we were looking at moving into one-dimensional data, so we looked at a number of ways of representing that data, in particular looking at the quantile function and how that quantile function can be related to other things that you already know about, like box plots and in particular histograms. And so today I want to focus on histograms for at least one lecture. And I want you to think about this as a histogram is actually a picture, as we saw last day, of the density. Remember, the bars of the histogram effectively are recording the slope of the empirical distribution function and hence approximating that first derivative and so the density. So think about a histogram as actually now an estimate. So it's a picture that is an estimate of the density. So we're going to look at some data here. This geyser data we looked at last time. Remember, we had two modes we saw in the quantile plot. You can get a histogram fairly straightforwardly in R, just with this hist function. Something you may or may not be aware of is this width function, which uses that data frame and then allows us to refer to the variates in that data frame by name alone. Okay, so a histogram of the geyser data looks like that. And so when we look at that, we're going to be decoding information there. And what information are we decoding? Anyone? First, just on the heights of the bars. So nobody wants to answer such trivial questions, right? So we're just looking at the height of the bar. That's sort of the length of a bar, looking at comparing lengths. They're on a common aligned scale, or alternatively the position of this height along a common aligned scale. So I want you to think about those perceptual tasks that we talked about in the first couple of lectures whenever you're looking at any of these graphics. So that's what we're trying to decode, but we're also getting a sense of the shape here. We see these two bumps, these two modes from the default histogram. We could change the breakpoints. Where are the bins? Where do the bins have their boundaries? And we just give that as the breaks to this as the breaks argument to the hist function. So we can get something like that. So I actually have different width bins, and you notice that no longer on this vertical axis is the frequency. We're no longer looking at counts, but we're looking at densities. So reinforce that this is an estimate of the density. And to be a density, the area under the curve, as it were, this curve has got a lot of little flat spots, little plateaus, that area has to be 1. Okay? So that allows us to change the widths, have different widths altogether, as long as we have the height reflect the actual proportion of data that are in that bin. Okay? If it was just frequency, it would look very different and be quite wrong. All right? So, in the histograms, what's changed? Well, we changed the widths of the bars, which was intentional, and that changed the heights of some of the bars, and the label on the vertical axis changing from frequency to density. So what I want you to think about is that the bars are intended to convey the density in any bin. So how many points are there? What proportion of the points are in that region? So I'm going to get a little technical here. If you've got these slides online, they're available now. It's probably a good idea to have them in front of you. So what we're looking at is if there are K bins, capital K, 1 through capital K, and the bins are called AI, I through 1 through K, and they have some width WI and height NI, the frequency, then we know that this sum, if we just had the frequencies, that would not sum to 1, so we have to divide by something. So in particular, we're going to look at a lot of things that have the same width. So if we have all of the same width, say W, the sum is going to look like this, HN, which means every frequency in every bin I'm going to have to divide by HN so that this thing actually adds up to 1. Right? Okay? So I'm going to have to divide the bar's height by HN, the count, in order to get a density. So now we've got something that looks like a density, and it's as trivial as that. If there were different widths, we would have to divide each interval by a different amount. Okay? So We can force that density scale just by argument, say that I would want it to be on a density scale. That's my preferred choice for a variety of reasons. And I can change the starting point. So let's say I've got the bins here. I'll stick with that width, h, whatever that is. Looks like it's a half. And I'll change where the bins start. Right now they're on natural boundaries, a half, 1, 1.5, 2, etc. But we could change that to start anywhere. And I'm going to do that by introducing the brakes. And I'm going to start from some specified value start up to 6 in size 0.5, so constant width bins. And I'm going to look at a whole bunch of these guys. So in R, I'm going to give you an array that's 2 by 3 of plots. And this is just going to produce several histograms. So those are 5 different histograms, same bin width, same density scale of the same data set. And you can see there's some bit of difference between them in the sense, for example, that in this first one we have 2 modes in both of them. Where those modes exist depend on the binning and the magnitude of the modes. So if you look at this leftmost mode up here in the top left compared to down here, it's shifted slightly to the right. Similarly, this one is now much larger, much higher. Looks like it's more concentrated than over here. So what you see may depend upon this relatively arbitrary thing, is where did you start the bins? Okay? So something as simple as that can change your perception. That can be seen pretty dramatically if we look at this with an interactive graphic. This is the Loon package, which you can install from CRAN. Just install packages Loon. And it's going to look a lot like the base histogram, except it'll be L_hist with the duration and some other things that are telling me that I want density scaling. And I'm going to show a bin handle. So let me just escape this for a minute and show you what that code looks like when we execute it. So now I've got these histograms. That's the waiting time between eruptions of Old Faithful, and that's the duration of the eruption. And I can, these things are interactive in that I can select bits of this. So I can say, well, let's look at this mode where the duration is very short. Select that and see that that corresponds to long waiting times over here between eruptions. If I'm looking at the short waiting times between eruptions, looks like I get long durations. Okay? So you want this kind of linking between plots. That's getting us up to actually a second dimension, which I don't want to talk about at the moment. So more importantly, there's this little bin handle here, and I'm just going to exaggerate the bin widths. So by pulling this, so now the bin widths are that large. And you can see the effect of bin width and just moving the edge of the bin. So it's kind of worrisome that there's that much variability in what you see depending on where the bin boundaries are, right? So we'll just go all the way through this. So the bin boundaries are kind of arbitrary and perhaps something that we would prefer not to be so dependent upon. There we go. So you can play with that yourself. So let's look at some theory here for histograms. So the notation here, you may want to jot down some notation so that you can just keep track of what we're talking about. The AK is the bin, the kth bin, and it's going to go from closed on the left, open on the right, from TK to TK plus 1. And suppose that these differences are identical for all K. So the H is the bin width. And now if I have NK observations appearing in the kth bin, I can say, well, what does this estimate look like? for any x. So if x is in AK, then my estimate of the density is going to be the same for every x value in that bin. It's just going to be how many points do I have in that bin divided by n times h to make it a density. Okay? So that's my density estimate for x in AK. And of course that'll be different for every AK depending on what will be changing is NK. But the corresponding estimator, if I was thinking about doing this over and over again, resampling from the same distribution, I want to think about what are the distributional features of the histogram estimate. So the estimator corresponding to that is going to look like this. So if I have the same sample size, and I keep the bins the same, what's going to change is this NK, right? So this is the random variable, be the numerator. Question, what's the distribution of that random variable? What's the distribution of capital NK? It's the number of observations that fall into the kth bin out of n chosen. Anyone? Yep. Normal? Why? Well, no. All I'm doing is I'm rescaling it at an integer. I'm rescaling a non-negative number. So it can only take discrete values, so it's not going to be a normal. That's going to take anything from minus infinity to infinity. I happen to be rescaling it by nh, but it's really still discrete. Anything else? Yeah? Poisson? Okay, why? Okay, so that sounds like a very good suggestion for a model of what might be here is that it's Poisson. If it's coming at me and I just observe however many fall in this group. What you're not using, the information I told you, is that I'm fixing the sample size n. So Poisson, I could have 0 to infinity in that bin. Here I can only have 0 to n, little n. Got another choice? Yes? Is it binomial? So it's a binomial. So we've got n observations that are from some distribution, whatever that distribution is given by little f of x, the density. And some number of them are going to fall in the kth bin. So that sounds very binomial-like, right? You're either in the bin or you're out of the bin. So the number that are going to fall in is going to be with some probability. What's the probability associated with falling in that bin? I'll call it pk. What's the probability of falling in that bin? All you know is it's coming from some density f. Guy in the blue t-shirt wants to tell me something. Yep. Sorry? NK times, okay, that would be a good estimate of that probability. But what's the real probability before you've even seen any data? You're not sure? It comes from some density. Whatever that density is. Here's the bin AK. What's the probability of falling in that bin? Come on. What's the probability of getting a value between here and here? Yep. It's just that area, right? The area under that curve, under the density. So this is going to be a binomial random variable with sample size n, probability pk, and pk's got to be that integral. Okay? That means you can get the expectation, you can get the variance of this. What's the expectation of a binomial? NP, okay, so that's just going to be NPK. What's the variance or standard deviation of a binomial? So the standard deviation is going to be the square root of the variance, npk times 1 minus pk. And that means, if I know that, for any x, I can think of this estimator and evaluate what its bias is. And the bias is just the expected value of the random thing minus the thing you're trying to hit. So that's our target. That's what we're using, and here's the average of it. How far away are you from, on average, from the target? What's the expected value of f tilde of x? It's going to be the expected value of this ratio, right? And 1 over nh is a constant. It's nothing random there, so that comes out of the expectation. And we know that the expected value of nk is npk. So the bias we already have. It's going to be pk over h minus f of x. So at any x in that kth bin, we've got the bias. Questions? Everybody knows what bias is, right? Good. So what happens as n goes to infinity? We get a bigger and bigger and bigger sample size. What happens to our bias? What's the math telling you? Come on. Fourth year. Do you see n in there? So if I let n go to infinity, what do you think is going to happen? Nothing. Right? That's not going to change. So the question is, when is this small? When would that bias be small? Well, that bias is going to be small whenever pk over h is nearly f of x, right? For any x in that k thing. So, or when pk is nearly h times f of x. So, if I've got that probability being in there is close to h being times f of x for the x that's inside that interval, then that bias is going to be small. If it's not, it's going to be large. And of course, what pk is depends upon h. Right? The smaller h is, the smaller is pk. The larger h is, the larger is pk. Right? Okay, let's look at the variance. So the variance of this estimator at a particular x in ak is just going to be the variance of that binomial, right? Which is 1 over that constant squared times the variance of nk. You know that's npk times 1 minus pk, right? So one of the n's cancels there. And I can ask you the same question. What happens to the variance as n goes to infinity? This is easier. What? Goes to 0. Hallelujah. Okay, so that's going to disappear, isn't it? It's got a greater sample size. This thing's not going to change very much. That estimator is going to be churning out the same stuff. So what happens as h goes to 0? Yeah. As h goes to 0, the variance will go to 0? Why? Kerblam, right? Well, it's not quite that obvious because we've got this pk and 1 minus pk here, and as h goes to 0, that pk is going to 0 too. So we have to be a little more careful. But this should blow up. So how are we going to be a little more careful? Well, let's look at the mean squared error. And the mean squared error is the expected value of the squared difference between the estimator and the thing you're trying to estimate. And you know, or you can prove very straightforwardly, that that's just going to be the sum of the variance and the square of the bias. So we can just plop those things in there because we've already evaluated those. So I've got the mean squared error. which is going to have a variance term and a bias squared term. And so if you recall from first year, right, there's a little bit of calculus that we can use to help us interpret this. And the real nuisance is this relationship between K and PK and H. And remember that the bias disappeared if PK was H times f of x. So that should look vaguely familiar, right? There's a rectangle there that I'd like to have as the same area. Do you recall some theorem from first year? The mean value theorem, which you thought you'd never see again in your life. So we remember that the mean value theorem is a funny thing saying something that looks intuitively obvious, but it says we can express this probability as this integral that we want as h times the value of the function at some value psi inside that interval. Psi k here for the kth interval. Okay? That there just exists something inside that interval that the rectangle built at that height, at f of that value times h will get you the right answer. Recall that? So that means if we look at the bias, it's pk over h minus fx. That means the bias is really this f of psi k, whatever that is, minus f of x. And that has the virtue of at least not having an h in it anymore. Right? So that bias we can see is equal to, well, remember it's pk in both, but you can see that that bias disappears as that h gets smaller and smaller and smaller because that psi k, the interval is getting smaller. Mean value theorem says it's got to be in that interval, and we're going to end up with a psi k closer and closer to the x. You can't be as far away from the x as that interval gets narrower. Okay? So the bias can disappear as as h goes to 0. So how quickly the bias disappears will depend on f at that value, of course. And to get a sense of that, I'll introduce something here that says, you know, if I look at the slope of two different values in that interval, of the f of x and f of y, let's say, and look at that slope, that can't really go off to infinity. That's a pretty mild assumption. Our density is going to be at least that well behaved. And that's called a, if you want a fancy name for it, that's Lipschitz continuity. So that means that if that's bounded by some constant, psi k, the slope, then I can look at this bias and say that's less than or equal to psi k times that difference, which is certainly smaller than psi k times h, right? Because that psi k is inside the same bin, so it has to be, can't be any farther away from x than the width of the bin. Any questions? Okay, so we've got that bounded, and therefore we know that we can let that thing go to 0, and the bias is going to go to 0. Similarly, for the variance, we can play much the same kind of games here that very simple mathematics that I've got pk is over nh squared is being multiplied by 1 minus pk. That's a number less than 1, so if I take it away, I've got something bigger than that. If I replace 1 minus pk by 1. And we know from that mean value theorem that that's equal to f psi k over nh. And putting this together with the bias means that our mean squared error looks like that. It's bounded by that amount. So the mean squared error of our estimate, of our histogram estimate for x in the kth bin is bounded by that amount. And now you can ask yourself questions like what happens to the mean squared error as h goes to 0, as n goes to infinity. So as n goes to infinity, what happens? Well, the variance is going to disappear, but not this piece, right? As h goes to 0, the second piece, the squared bias, is going to disappear, but this thing for sure is going to blow up. Okay? So the mean squared error is going to blow up largely because the variability is getting greater. So bias is kind of you're stuck with. Depends on h, but we can make h small enough to make that bias arbitrarily small. Variance, it's going to blow up as we make h smaller and smaller. So we've got a number of choices here. One is increase the sample size to be as large as you can possibly make it to make that variance small. But typically that's not a choice. We have this particular sample size and we want to be able to make a pretty good estimate. So we really want the variance of our estimate to get smaller. So how would you usually make variances get smaller? Well, have a think about that. Because we're going to use that in a few minutes. So the other thing is that if you really wanted this whole thing to get go to zero, you have to have n go to infinity and h go to zero at speeds relative to one another so that n times h goes to infinity. So histograms, how can we improve them? So my suggestion is that the way that you often reduce variation is by taking a whole bunch of different measurements of different estimates and averaging them. Okay? And I can think about, I know I've got different histogram estimates simply from moving where the bins start and end. Right? Just moving them along. So let's move this along, and I'm going to plot a bunch of different values over top of each other. So I've got some transparency here. And now these are 5 different histograms on top of each other, each one of which is an estimate of the density. And kind of if you squint your eyes on that, that looks a little more like maybe a density, sort of a continuous thing. Okay? You can also see some sort of variability here, and how variable is that estimate? How variable is the histogram depending upon where the bins begin? So what we've done here when we squint this and we look at it, we're kind of averaging these things, sort of smoothing out these histograms between one another. So let's make this a little more formal. So with in R, the histogram is actually will return a data object, right, that has particular structure. So if I do a histogram and I choose not to plot it, I can find the structure of that histogram. You see I've got breaks, where the breaks occur, where the bin edges are, the counts in each one of the bins, the corresponding density estimate, the middle of the bin, etc. So I could take these density estimates for 5 different histograms and average them. So I'm going to get an average of 5 different density estimates. And that should reduce the variability. May not change the bias very much, but it should reduce the variability. Bias will still be bounded. Okay? So here are our 5 that we had before, so I'm just marching over. And these are chosen in a particular way that each one is moving just 1/5 of the interval to the right. So the boundary is just moving 1/5 of the interval. So by the time I get back at the 6th one would be, I'm back at the beginning again. So at any x, if I want to know what the value of my estimate should be for x equals 2.25, I take the height of the density in each one of these 5 and average that. Give you that as an estimate. Okay? And I can draw that. So here's a function that's going to draw that. I'll leave that to you to look at at your leisure. But I'm going to call this ASH for average shifted histogram, or average of shifted histograms. And talk about how many histograms are we going to use. That will determine what fraction of the bin width I will move over. And that's kind of a long function, appears over 3 slides. At the end, I'm just going to plot the average at each one of these x's. So here we go. Those are our 5 estimates, and there's the average. So again, that average is now looking a little bit more like a density, like a continuous density. It's smoothed out, it's going to have less variation, or should have less variation than any of these other ones, because it's an average of 5. Okay? So I want you to stop for a second and think about what you knew from your first course in statistics about having observations and their variation being, the variance being sigma squared, and the average of them having variance sigma squared over n. And now what we're doing is we're looking at pictures. So these pictures are observations just as the others, just as a numerical value. And we think about averaging over these 5 different pictures. And we should be able to say something about it, that this should end up with we should be able to say something about the characteristics of that last estimate. Okay, any questions? So, I want you to understand the effect of averaging. So we're going to look into this a little more deeply, a little more mathematically. And what I've done is I've drawn the 5 different histograms here in different colors. So you can follow any one of these colors and you can see what the histogram associated with it is. And what we're going to be doing is taking the average of, at any point here, just look up and take the average of the heights at that point. That will be our density estimate. Okay? Questions? So what this means is that when I do this and I've shifted them over so that by the time I've gone m steps, let's say, over, in this case 5 steps over, I'm back to the beginning again. So I only have 5 different values. And it looks like all of these little bins, these tiny ones, are just 1/5 the size of the big bins. So it's as if those are little tiny, tiny bins. In fact, I want to look at any one of these intervals, the big bin intervals here, A0, and divide that up into the pieces. So if I look at all the bins here and I label them A0, A1, A2 up in that direction, A-1, A-2 in that direction, any one of these bins has got these equal divisions inside it. Okay? Question? Sorry? Well, each color corresponds to a different histogram, okay? But those are the boundaries of the different histograms. And now I'm going to say, let's look at these as tiny bins. So I'm interested in really this blue one from there to there, that's my A0. But I know the magenta one, it goes from there back and there over to here, etc. So I'm just going to use these boundaries because they're nice and equally spaced so that I know each one of these has the same width. Yep. Sorry? To draw this? It's in my our markdown here. I can show it to you if you want, but it's not that interesting. All I'm doing is our code that I'm drawing a histogram starting here, these breaks, right, with that color on the border, no color in between. Move over, draw it again with a different color. Just march it along. It's not that sophisticated. Okay? But pay attention to this. So any one of our bins, big bins, divides up into 5 smaller bins, determined by as we shifted the histograms over. So we're going to think about m histograms in general, but in this example it's going to be m equals 5. So I'm taking any one of our bins here and dividing it up into m small bins by those different shifted histograms. So if this goes from 0 to h, I know that each one of these things is width h over m, right? Which means this one goes from 0 to h over m, this goes from h over m to twice h over m, twice h over m to 3 times h over m, etc. And same in the other direction, if that's the origin. Okay? So I do have the coordinates of all of those tiny bin boundaries. Everybody with me? So suppose I've got these m histograms, f1 hat through fm hat. Each has a constant bin width h, but each has different shifted origins. Okay, so the first one goes 0 to h, 2h, etc. Second one begins at h over m, then goes h over m plus h over m plus 2h, etc. Down to the last one, m minus 1 over m h, adding h each time. Okay? So F1 has those boundaries, and F2 has boundaries that are slightly shifted by h over m. So what we have is this histogram, this estimate here, what we call average shifted histogram, estimate ASH, which is just the average of the m that you have. So wherever x is, it's the average of those values. And the corresponding estimator will be with a tilde over the top. Okay? Everybody with me? So it looks like this, and I want to figure out, well, how does that break into little pieces? How does it break into the little tiny bins? And so these histograms have identical width, but they're shifted by some small amount, h over m. And these little intervals, the big intervals were a's, the little intervals would be b's. Okay, so they're always going to have some width delta, which is just h over m. Okay, so these are the tiny intervals. Everybody with me? So those are my intervals marked there, the tiny intervals. So I've got many, many more of these. I have m times the number of intervals, right? So I've got all these little tiny intervals. And now I can figure out what does my average look like. Okay, so I'm going to average over all of these histograms. And what I want to do is count how many observations are in each of these pieces. So I know that there's nk in the kth big interval, but they're going to fall according to some pattern, whatever that is, in the small intervals. So for n0 in the 0th interval, maybe v0 up here in the first one, v1 in the second one, v2 in the third one, v3 and v4. And those sum to n0. Okay, so that's a notation. The v's are how many's in the little interval, and the n's are how many are in the big intervals. Okay? Everybody with me? Told you should be writing down some of this stuff, the notation, or you'd get lost in the sauce. So vk is the number of x's that are in the tiny little intervals, and I want to suppose that x is in this interval b0, just one of these little intervals, doesn't matter which one. Pick 0 just to make the notation simpler. So for every value of x in that interval, our average shifted histogram estimate is just going to be the average of the histograms that cover that bin, the value that covers that bin, okay? So we have to get the count from every interval, from the interval in every histogram that covers B0. So what does that look like? So this is so I'm looking at B0 is this interval here, where it says V0. And the first histogram we looked at covers that. So it's going to have the count that's in the first histogram is going to be V0 plus V1 plus V2 plus V3 plus V4. The next histogram, which is shifted over one here, well, the part that's going to cover it is just this bin. So the count that goes into that is V0 plus V minus 1 plus V minus 2 plus V minus 3 plus V1, right? And similarly, if I'm shifted over 2, it's going to be V1 plus V0 plus V minus 1 plus V minus 2. And one that we can actually see everything on here, this one is going to have V minus 1 through V3. That sum is what that histogram is going to be contributing. Make sense? So what we're saying here is that this particular interval of F2 hat overlaps and contains those points. This is general with general M. So for each one of these guys, we can talk about what are the values that cover that. What is going to be the height of that histogram bar? Okay. And now our estimate is going to be the average of the m counts, right? So if I've got m histograms, I'm going to have the average frequency, as it were, in that tiny bin by averaging over those m counts. And lastly, to make it a density, I still have to divide by that NH. Okay? So in fact, every histogram, if it was a density, was divided by NH in the first place. Any questions? So that sort of makes sense. So we're just shifting over and seeing which guys are in, what's the count. Okay. So that means we can actually sort out, just taking the sums here and dividing by NH, what we're adding up to average. There are m of these things. We're going to average these, divide by m. Get a histogram. We can figure out what's in there. And this is again, so V0 to Vm minus 1 here. And then starting here at Vm minus 2, going back to V minus 1. Starting here, going back. That's what all of these pieces are. So it's just adding them up. So the notation follows. And you notice, for example, that V0, since that's the interval of interest, appears in every one of these sums. Okay? So V0 appears m times. V1 minus m out in the far end is only going to appear in one of them. Vm minus 1 is only going to appear in one of them. Vm minus 2 is going to appear in two of them, etc. Okay, so you can actually turn that into something that we can average. So there's the sum. I need to divide that by m in order to get an estimate. Any questions so far? Okay, so I can just rearrange these terms as, noticing, as I said, that V0 appears in every one, V1 appears in m minus 1, right? V minus 1 appears in m minus 1 of these things. So this is just rearranging all of this. Or just to make them line up, mv0 plus m minus 1 v1, or m minus 1 times v minus 1. So they match perfectly like that. Okay? So dividing that by m gives us our estimate f hat x with a parameter m here. That's our choices. How many divisions do we want to make for any x in that b0, that tiny interval. So our general expression then of this average shifted histogram can be written like this. I'm going to take all of that thing, I'm going to divide by the NH and average. So that's going to be a density. Okay? Is that clear? Very straightforward, I think. It's just a lot of notation. But if you understand the pieces, all we're doing is adding up the contributions from each bar, from the bar, appropriate bar for each histogram. Okay? Questions? How many people are lost? There's a lot of people doing the Queen's wave. Are you lost? Question? Can you formulate a question? All right, let's just one more time, but with feeling. So I've got all of these histograms, right? And all I'm doing is looking at one of these little particular tiny pieces. And I know that there's N0 in this big histogram, right? Because this is just my base histogram. My next histogram is going to be the same thing, it's just to shift it over a bit, right? So the next histogram will have these V1 through V5 sum to its value, and V0 to V minus 1, V minus 2, right down to V minus 4 in the next bar. Okay? And if I have 5 histograms here, and I'm interested in the average of the bar heights for every histogram that overlaps this little B0, I could, if I knew these little values on these tiny bins, I could tell you what the average is going to be. I'm going to have to sum up all of these for that one. I'm going to have to sum V3 to V minus 1 for the next one, V2 back for the next one, etc. Okay? Anybody lost on that part? If I do that, and I turn it into a density, so I'm dividing by NH, that's just what the pieces are. That's just what they add up to. Now I'm just ordering them. So this is the piece, that's my F2 hat, F3 hat, and this is the one I started with down here, my F1 hat. That's the height in densities, right? But I have to take this whole thing, since that's the sum of them, divide by M to get the estimate, get the average. So rearranging the terms, I can do this, and that's just algebraic manipulation. That it's got this lovely pattern, m, m-1, m-2, etc., down to 1, as we go from 0 up to m-1, m-1 at -1, and down to 1 at 1 minus m. Okay, so that means our estimate looks like that, which is arguably kind of nasty and not easily interpreted. But if you think about it, I'm going to take these NH inside here, but every one of these I can imagine a sum that's going from 1 minus m here, back. So this is for the kth bin as opposed to B0. Imagine k was 0 here, but going m minus 1 back to 1 to 0 that I'm adding to k, and back up again to m minus 1. So that's just another way of writing what we've got here, is that I've got this sum of these little counts. I'm interested in the kth position, the kth tiny bin, and I'm looking at what seems to be a weighted average of those little counts. Okay? These look like little weights. M minus the absolute value of I over NH will give you these values. Okay? Or alternatively, take this M through and the NH out, and I've got 1 over NH, that's our nice thing for making this a density, and I'm summing for all I less than M of 1 minus absolute value of I over M times VK plus I. So if I'm interested in the kth bin, that little BK, right, what I need to do is go from minus M to plus M, I guess minus M to plus M away, and get the counts in each of those little bins. And I'm going to add them together as a weighted average. And what does that weight look like? Well, the farther away I get, the larger this value, so this decreases. So I've got a decreasing weight. So I'm going to use the counts at bins farther away, M away on this way, M away on that direction. But I'm going to have the counts appear with weight that is greatest at the bin I'm interested in and least at the bins that are far away. And so you can actually plot that with a little bit of R code, and it looks like that. So this averaging should be giving us a clue of how we might actually make estimates of density. I'm interested in estimating the density here. So I'm going to estimate that density by giving weight 1 to the count that's inside this little bit, and weight slightly smaller to the count that's in here and here, smaller again to here and here, right? Just 1 over m, right? 1 over m times how far away we are. So we see that that's decreasing this kind of triangular weight function. And that sort of makes intuitive sense. If you want to estimate the density in this area, you probably should really count on the points that are close to it, and maybe the ones that are a little farther away but still close. But you shouldn't depend too much on the ones that are very far away. Right? So we're going to use this average of these M histograms is really a weighted average of counts that are nearby the x of interest. Okay, so some funny things are happening here. One is, this is just a plain old histogram which you've been drawing since time immemorial. It's got a lot of variability in it that we can actually quantify mathematically. In fact, it's an estimate. It's an estimate of the underlying density that generated the data. Okay? We can talk about its mean and its variance. We can talk about its mean squared error. And we can use the usual tricks just because this is graphics doesn't mean we can't use the usual statistical tricks of averaging things. That averaging thing is not going to do much with the bias, but it's sure going to reduce that variance. It's going to be just like sigma over root n, right, for just averaging things. And then finally, when we do that average and we look at this, it has this other interpretation. If all you care about is the density at a particular point x, use the count of the points that are nearest it, and then the points that are farthest away with slightly less weight, farther away, slightly less weight, etc. So this nice triangular distribution. And if m was larger, this of course would go out farther, use up more of the points. It would be a little smoother. We can actually still go down here because we have the same bin width, but it would be a little smoother. So in the limit, you can actually think that what we'd have is just a triangular weight function if we can make m infinite. Okay? Any questions?